Today we're talking about graphing rational functions. But first I want to talk about why we cannot divide by 0, why that's sort of a illegal move in the math world. So if you look at this chart right here, we're just taking 1 divided by x and seeing what the result is. As you can see, as x is getting smaller and smaller and smaller, where the value of x is really approaching 0, you can see that the y value is getting larger and larger and larger and larger. And so when x actually is approaching 0, the y value is actually approaching infinity. But there is no exact number for dividing by 0. And so we end up getting, when we're talking about the graph, we end up getting sort of an asymptote. And so let me just show you real quick what the graph of this particular function looks like. So when we have y over x, and this is just a really quick sketch of this. We get a graph that looks like this, which is referred to as a hyperbola. We're not going to get too much into the names of this graph, but we are going to be examining the nature of the graph and how to actually graph this function without using a calculator. And so we can see that when x is 0, the y value right here is approaching infinity, and over here it's approaching negative infinity. So I'm going to talk a little bit about a graph being continuous and discontinuous. These are the graphs that we've talked about so far. So when you have a continuous graph, that means that you can take your pen or pencil and you can follow it along the graph without having to pick your pencil up at all. So this linear equation is continuous. This parabola is also continuous. And this cubic function is continuous. And so again, it's when you follow along on a graph with your pen or pencil and there are no holes or breaks at all. So a graph is discontinuous if it does have a hole or a break. So for example, this graph right here, there's a hole in the graph. So you would follow it along with your pen or pencil, but then you'd have to pick it up to continue with the graph. Same thing over here. There's a break in the graph. So I have this function over here and I'm following it along. But if I want to continue following along, I have to pick my pen up to then continue with it over here. So that would be discontinuous at whatever this x value is or whatever this x value is. If somebody can remember, we'll do this activity in class, walk halfway to a wall. So try to remind me. So there's a difference between finding an asymptote and finding a hole in the graph. So when we look at this function right here, f of x equals x over x minus 2, I'm going to take that denominator and set it equal to 0 to see where is this function discontinuous. So I have x minus 2 equals 0, and I'm just going to solve for x. So x equals 2, and that's where this particular function is discontinuous. And for this particular function, it's actually a vertical asymptote at x equals 2. And so this function looks like this. And you can see in your calculator, but we're actually going to be doing a few things without your calculator. So we can just kind of look at the nature of graphs. So when x is 2, that's where we're going to have a horizontal asymptote. And so I think that you've heard the term asymptote before. An asymptote is where the function is getting closer and closer and closer to that value, but never actually hits that value. So this is what this function would look like. And so sometimes we have a vertical asymptote when we look at the denominator. Sometimes we have a hole in the graph. So for this particular function, it's an asymptote. So we would say that the vertical asymptote is at x equals 2. However, sometimes it's a hole in the graph. And so now I want to talk a little bit about finding critical values. So if there's an x in the denominator, there will either be a whole or an asymptote somewhere in the graph. So you can take a minute to write this down. You can pause it if you need to. This just kind of gives us the procedure for finding critical values. So we're going to set the denominator equal to 0 and solve for x. If we factor it out and there's a factor that divides out, it is actually going to be a hole in the graph instead of an asymptote in the graph. So we'll talk about a little bit more about that in the next example. So this is a common theme for this unit. Always factor if you can. So we've talked about that in everything we've done so far in this unit. Factor, factor, factor. And so that's what I'm going to start with. I'm going to factor in the numerator. Except I didn't, did I? I just rewrote it. Duh. Let's try that again. I'm going to factor the numerator. And so I have the difference of two perfect squares, x plus 3 times x minus 3. And as we can see, we can divide out a factor of x plus 3. And so we just get f of x equals x minus 3. But if I follow what that procedure was for the critical values, the first step in that procedure was to set the denominator equal to 0. So I'm going to do that. So the denominator is x plus 3. I'm going to take that and set it equal to 0 and see that x is equal to negative 3. Because the denominator factors out once you factor in the numerator, we say that there's actually a hole in the graph at x equals negative 3. So when you go to graph this function, and I'm going to ask you to do that in your calculators right now, pause it and graph this function. So there's a hole at x equals negative 3. It's going to look like a straight line. It's going to look like a linear function that follows this equation right here, x minus 3, f of x equals x minus 3. But I don't know if you could zoom in. I think you can zoom in enough to see that there's actually a hole in the graph at x equals negative 3. Or you can look at your table of values and you'll see that when x is negative 3, there's an error. That word was error. I don't know what happened with my voice just then. So you're typing in this original function into y equals, and then either look at the graph and zoom in at x equals negative 3, or look at your table of values. And for this one, there is no vertical asymptote. So then we're going to talk about finding a horizontal asymptote, and there's a few different things that you can do for this. You can either plug in a really big number for x and kind of see where it's heading, or you can think of end behavior. And we've talked a little bit about end behavior. And so for number 3, I'm just going to take a really large number. Let's say we take 1,000. And substitute it in for x. We can kind of see where this function would be heading. And so if we divide this out, I don't know what this is off the top of my head, so hold on just a sec. All right, so I'm going to take 2 times 1,000 over 1,000 squared minus 4. And we get 0.002. And I think it continues a little bit there. But we can kind of see that this value is approaching 0. And the larger number you plug in for x, the more obvious this will be that this value is actually approaching 0. So we would say the horizontal asymptote would be at x equals 0. And we'll certainly talk about this a little bit more in class. So if you're more of a rules person, here is some rules. And again, we're gonna really talk about this in class, but this kind of gives you guidelines for horizontal asymptotes as far as what do you have in the numerator, what do you have in the denominator, what does that mean for the horizontal asymptote. And so I would pause it here, write that down, and then here's the rest of it. So you can certainly follow those guidelines as well. So now it's your turn. I'm going to give you two problems, and I'd like for you to look back in your notes of what you just wrote down and see if you can figure out whether or not there's a hole, whether or not there's a vertical asymptote, what is the horizontal asymptote. So here's number 1, and here's number 2. And we will talk about all of this in class. See you then.